Thank you very much. And also thanks a lot to the organizers, both for the invitation and for taking care of us very nicely. Thanks a lot. To start off with, I'm going to give the definition of a contact sub-Riemannian manifold, and then afterwards I show some pictures so that hopefully it won't be too abstract in case it's the first time you come across this. So what a contact sub-Riemannian manifold consists of, it's a triple MDG, where M is a smooth manifold of odd dimension, and I will refer back to the N later on, and keep in mind that the N is the one, so that the dimension of the manifold we look at is 2n plus 1. Then D is going to be a contact structure on M, and I'll say a bit more about this in a moment, what this actually means. But then observe that the pair MD is now a contact manifold. So that's why the word contact appears in the word. And then we assume that G is a smooth fiber inner product on D. So essentially we have ways of measuring tangent vectors which lie in the distribution. And now it turns out that MDG together forms a so-called sub-Riemannian manifold because this contact structure D is going to be a completely non-integral distribution on the manifold M, and then with the G, this gives you a sub-Riemannian manifold. But like for the rest of the talk, if you've not heard of sub-Riemannian manifolds before, don't worry about it. Just take this as your definition. And to highlight what is meant by that D is a contact structure in M, so it's going to be a rank 2n distribution on your manifold of dimension 2n plus 1. And it's generally given locally as the kernel of some sort of form of one form omega, which satisfies a certain non-degeneracy condition, which in this case is that omega wedge d omega to the n, where remember n was defining the dimension through 2n plus 1, that this is non-zero. And as I said, usually you assume that your distribution D is locally the kernel, or like is the kernel of some local one form. But we will assume that there actually exists a global one form omega on M, so that your distribution is of this form. And the reason why we're assuming this is that the moment you have a global one form, you induce an orientation on your manifold M, which will be very helpful throughout, because this then defines a volume form on N. It's non-degenerate by assumption, and this will sort of sort out a few subtleties if you just assume that you have this global one form. And then one last thing to highlight is, I'm not going to give the exact normalization condition, but basically, so you have a certain choice of how you choose omega a priori, because your distribution is just given as the kernel. So think you multiply omega by some positive function, or a function which is positive everywhere on M, then this changes this one from omega, but it still satisfies this non-degeneracy condition. You still end up with the same distribution. So a priori you have a choice of what omega to choose, but there's a way of, or you can impose a condition so that your omega is linked to the smooth fiber inner product you choose. So the thing to take away is that if you fix your M, D, and G, you then have like one canonical omega associated to that. So every time I have an omega appearing later on, I don't have a choice. It's uniquely given by the contact sub-Riemannian manifold I start off with. Yeah, essentially. You then also... Exactly. Yeah. And basically what to say, what we ended up with, if you take a manifold of dimension 3, then your contact structures play its field of planes on your three-dimensional manifold, and they're set up in a way that you are completely non-integrable, which you can think of that if you start at some point, you can serve along those planes so that you end up at any point in your three-dimensional space. And basically that's the setup we have. We have an odd-dimensional manifold with a field of hyperplanes, which are completely non-integrable, so some form of this. And what we're now interested in is to study hypersurfaces in this space. And I should say that at some point the aim would be to study hypersurfaces or like surfaces of any codimension in sub-Riemannian spaces. But because sub-Riemannian spaces are so vast in terms of what can happen, this is kind of maybe step 2 now, because in the contact world a lot more is known. Okay, and now just, as I said, in case it's the first time you heard anything about that, one very nice three-dimensional contact sub-Riemannian manifold is the Heisenberg group. So you have this contact from omega in R3, which if you take Cartesian coordinates x, y, z in R3 is given of this form. And you can check that it satisfies this non-degeneracy condition. And then you basically, your plane, so your contact distribution is given by the kernel of this one form. And the smooth fiber inner product on the induced contact distribution is of this form. So you don't have like a Z component appearing in here. And now, if so take your Heisenberg group with this contact structure on R3, and now consider a sphere in this space. Now there are a few things which can happen is at every point on your sphere, you have a tangent space to that sphere, and you also have the hyperplane, the contact plane coming from the contact structure. And in here, you can see that this blue thing is the contact plane. And almost everywhere, it gives you the tangent space to the sphere and the contact plane intersect in a one-dimensional subspace. And this then gives you this line foliation on this sphere. And the two exceptional points are the north and the south pole, because you can check that there, your tangent space coincides with the contact plane. And they turn out to be the points where subtlety arises. And another image is if you take the parabola, or the paraboloid in, again, the Heisenberg group, you get this line foliation induced by the contact structure, and you have one point, in this case at the origin, where again the contact plane coincides with the tangent plane. And one thing to highlight how the three-dimensional case and all the higher dimensional cases differ is that if you look at this space and remove this point, then there's no way of changing the line or the leaf you're on. Like if you start off at this leaf, you can like sort of walk along this leaf if you want to stay like on your surface and only move in the contact directions. And then the only way you would possibly be able to change is by going through this point. So the moment you remove that point from your space, you don't have sort of you can't move from that leaf to that leaf. And similarly here, if you remove those 2 points, you cannot change the leaf you're on. And that is if you have this this rank 2 distribution on your three-dimensional space, then this always induces an integrable line field on your surface. And this is something different compared to what happens in higher dimensions, because there the distribution you end up with on the hypersurface is actually going to be completely non-integrable. That's just something to highlight, but it won't be needed for the rest of the talk. But there's like an interesting subtlety, a difference between n equals 1 and n strictly bigger than 1. And another thing I should highlight is that if you just go metric-wise, then from this to this point down here, this path has finite length. If you just use this fiber inner product in finite time, you can end up at this point down there. And these special points, Tommaso has mentioned them in his talk, are called characteristic points. So if you, as I said, you have your hypersurface S, which you consider embedded in your contact manifold MD, then everywhere where the tangent space to the hypersurface coincides with the contact plane, then this is called a characteristic point. And basically those are the points which are not particularly well understood, and we try and put some effort into like getting a better understanding of what happens around those points in terms of the dynamic. And then one work we've done was to, we want to induce a stochastic process on these hypersurfaces. And to do that, we essentially construct a second-order partial differential operator on the hypersurface. And once we have that, this canonically induces a stochastic process. So that's why I now continue by giving a construction for a second-order partial differential operator on a hypersurface S in this contact manifold MD. And to do that is, remember that I said this omega induces this volume form. And because the omega is like given uniquely through your contact sub-Riemannian manifold, this is like this unique volume form. And what I now do is you can make sense of a so-called sub-Riemannian normal vector field to your hypersurface. And if you do that, we now use this volume form, which is given on your manifold M. And we use the sub-Riemannian normal vector to the hypersurface S. And if we do the restriction of this volume form to the surface, we end up with a volume form induced on the hypersurface. And the one thing I should highlight is that this normal, sub-Riemannian normal, is not defined at characteristic points. So something goes wrong at those characteristic points, which is why this expression only makes sense on the hypersurface minus the set of characteristic points. So this mu is really just the volume form on the hypersurface minus the characteristic points, but that's fine because the set of characteristic points is a closed set. So if you take a hypersurface and take away the set of characteristic points, you're still left with a well-defined hypersurface. And now we have a volume form on our hypersurface, which means we can just do the usual diff-grad approach to define a second-order partial differential operator on your hypersurface minus characteristic points. And here, so if you have a completely non-integrable distribution on your space, you can make sense of a, in a way, horizontal gradient. So that's absolutely fine. And now we identified a nice measure on the hypersurface to define that. And now I want to say a few things about what happens with this second-order partial differential operator and what happens with the stochastic process. So going back to the example we looked at early on, so that was the paraboloid in the Heisenberg group, and you can do computations and show that your this Laplacian or sub-Laplacian is given of this form where the coordinates are defined as follows. So S is going to be like arc length along this leaf, and then this psi essentially identifies what leaf you're on. So psi runs between 0 and 2 pi. That indexes this the spiral, and then S is just the arc length along the spiral. And you can check that this intrinsic sub-Laplacian, which we defined through this diff-grad method, exactly takes this form. And now, if you want to define like a stochastic process, you generally go for 1/2 of something. So similarly for Brownian motion, if you have your Laplace-Beltrami operator on a Riemannian manifold, then the Brownian motion is the stochastic process whose generator is 1/2 of the Laplace-Beltrami operator, which is why the canonical thing to go for is this generator. And if you now look at this from the stochastic side, what happens is that this induces the random dynamics where you're, say you have a deterministic starting point, then it's going to be on some leaf, say we're on this leaf, and then the process induced is a so-called Bessel process of order 3 on this leaf. And as I said earlier on, when you take away your characteristic point, this point down here, then this is the only point where you could possibly change the leaf. And it turns out that this is a stochastic process which never hits the origin. So in this case, the origin on this leaf corresponds to this characteristic point, so-called Bessel process of order 3, and it's known that this essentially arises if you take a Brownian motion in R3, take its norm, or there are two ways. Either you take Brownian motion on a line and condition it to never hit the origin, then you end up with a Bessel process of order 3, or if you take a Brownian motion in R3 and take its norm, you also end up with a Bessel process of order 3. And in both cases, you're guaranteed that you, with probability 1, never hit the characteristic point. And that's interesting in a way that even though metric-wise, you can get to this characteristic point in finite time, if you look at this sort of intrinsically induced stochastic process, you don't end up at the characteristic point. You never hit it in finite time. Okay, so that's one example. And then the other example I showed early on is slightly more complicated. Again, we go for 1/2 of this operator. And here, in this drift term, you have like an elliptic integral of the second kind appearing. It's a bit annoying. But you can still show that you're never going to hit, like if you start at a leaf, you're never going to hit the north or south pole. So you're going to be confined to this leaf for all time. But maybe the more interesting thing is when we looked at this expression, so I should say that everything which happens in 3 dimensions is joint work with Davide Barilari, Ugo Biscayne, and Daniele Canassa, and that's been available for a while. And everything which is going to be in higher dimension is joint work with Davide Barilari, which hopefully will be available soon. And when we looked at this expression, it turns out that it's very close to another very nice stochastic process, which is the Legendre process, which is if you take a one-dimensional Brownian motion on an interval and condition it to never hit either of the endpoints, then you end up with a Legendre process, which is also like confined to this interval for all times. And this generator is very close to Legendre process. So then the obvious question was like, is there any way of really recovering the true Legendre process? And it turns out that you can do that. And for that, this is kind of, now this so-called example gives you more or less the model cases in the 3-dimensional case. So what happens is we consider the Heisenberg group, which I introduced early on. And now you can also consider SU2 and SO2R as 3-dimensional contact sub-Riemannian manifolds. And basically what happens is, in all 3 cases, because they all have an underlying group structure, you can find left invariant vector fields x1 and x2. Their bracket gives you a third vector field. And then the way those 3 model cases differ is basically in terms of this kappa. So if you now consider the bracket between x0 and x1, you obtain some multiple of x2. In the Heisenberg group, this is just 0. In SU2, this is positive. In SO2R, this is negative. And essentially, for instance, in SU2, if you think in terms of your usual group structure, there are 3 left invariant vector fields. Take any 2 of those, rescale them correctly, and you get the third one out. And then similarly for SO2R, you just there have to be a bit careful which of the 2 left invariant vector fields you choose. But you can do the same thing. And now you can choose a canonical surface inside those 3-dimensional contact sub-Riemannian manifolds. And so this is the fancy way of writing it down. Essentially, what this amounts to is in the Heisenberg group, it's just the plane, the horizontal z equal to 0 plane, which is a limit case of the paraboloid we already looked at early on. In SU2, what happens is you have S2 embedded in SU2, which is basically S3. And in SO2R, you also end up with something which is like a horizontal plane. And then, in these cases, you can compute that this that this intrinsic sub-Laplacian is of this form, where now the R was what I called earlier S. It's the arc length along your leaf. So what happens is that in the Heisenberg group, when we had our plane, we have one identified point, and then r just gives you the distance away from this point. In the sphere, we have, very similar to the example I showed in the Heisenberg group, we have two characteristic points, and then your r moves on an interval between like 0 and this pi over k. And then in the SL2R case, you again have some sort of horizontal plane where your r just runs from 0 to infinity. And what you obtain is, this is your essentially drift term, expressions of this form. And if you look from the stochastic side on this, you basically recover three very familiar stochastic processes. So I already mentioned the Bessel process of order 3. That is the process we obtain in the Heisenberg group, if you consider the horizontal plane in the Heisenberg group. Then we have this Legendre process of order 3, which I say you can obtain by taking a Brownian motion, which you start at some point in an interval and condition it to never hit either of the endpoints. That's where you obtain a Legendre process. And then there's something which is called a hyperbolic Bessel process. It has this generator. And you notice that it's always of order 3, of order 3, of order 3. And we kind of wanted to understand of where does the 3 come from? So what are we seeing in here? Which is why then, as I said, jointly with Davide, we were trying to push this to higher dimensions and see what happens with the 3 in that case. And another thing I should highlight is all of this work in three-dimensional case, we actually obtained this, what I introduced earlier on, this intrinsic sub-Laplacian through a limiting approximation, which if you go to higher dimensions is getting more and more complicated. So that's why David and me came up with this intrinsic construction where you define your measure and then take this diff grad to get a much better control over this second order partial differential operator, which you want to use as your generator for the stochastic process. And so if you push this to higher dimensions, the important thing essentially is to understand how this measure mu behaves. And it turns out that the model cases are a bit not particularly concrete, but I'll try and give the main ingredients. So we want to play a similar game as we did in the three-dimensional case. So in the three-dimensional case, we had like something like the Heisenberg group, which you can think of sort of a zero curvature space with this kappa equal to 0 because this has some sort of curvature invariant property. We think of this SU2, which is the same as S3, as the positive curvature space, and SL2R as the negative curvature space. And here it's also important that SL2R can be thought of as a particular hyperboloid. So takeaway is like, you've got an Euclidean space with a contact structure, you have a sphere with a contact structure, and you have a hyperboloid with a contact structure. So we want to play exactly the same game, and this can be done. So you can equip odd-dimensional Euclidean space, odd-dimensional sphere, and a particular odd-dimensional hyperboloid with a contact structure. So if you then take a hypersurface in those spaces, which is going to be like essentially 2n-dimensional Euclidean space, sphere of dimension 2n, and a particular hyperboloid of dimension 2n, and then the measure induced through this restriction of the volume form induced to the contact form is of this form. And now this looks like hard to digest, but the important thing is, so we again have some sort of parameter k appearing as we had in the three-dimensional case, and these are the expressions for this hk depending on what space you're on. And if you stare at this expression for long enough, I should also highlight that I'm leaving out a constant which is only affected by what normalization condition you impose to link your smooth fiber inner product and your contact form. So this is subject to a constant. But yeah, so if you look at this expression for long enough, then, so remember we now have a volume form in a 2n-dimensional space. And if this 2n was a 2n minus 1, it would be exactly the volume form, subject to constant, you obtain on Euclidean space, sphere, and hyperbolide. So what happens here is that we have one additional factor of R, of this sinus and this shine. And that's one thing which changes through this sub-Riemannian construction. So we now have like a 2n-dimensional space which comes with like one extra factor compared to what you'd expect in the Euclidean construction. And if you translate that, you can check. Basically, if you now use this measure to construct your sub-Laplacian, the thing which appears in your drift term is, because all of this, one thing to highlight is we now don't go for the full sub-Laplacian, but we want to understand how your distance away from the characteristic point evolves. So this R again is in a way a radial component. This is now not a component on leaves, because I said earlier on you can now freely move in the entire space. Well, not freely, but you can move in the entire space. And but we want to understand the distance away from the characteristic point, as we did earlier on. And then the drift term for the associated stochastic process is essentially the derivative of that expression with respect to R divided through by this. And then what you obtain is your B is going to be of that form. So it's very similar to what we had earlier, except we now have this additional n in here, because earlier on the n was equal to 1. And now what this tells you on the stochastic side is we obtain a Bessel process of order 2n plus 1, Legendre process of order 2n plus 1, and a hyperbolic Bessel process of order 2n plus 1. So that's where the 3 came from. And the thing to highlight is again that, for instance, take this. We had our hypersurface is of dimension 2n, and the radial process in this geometry is a Bessel process of order 2n plus 1. And you again see this gaining an order, because if you just take Brownian motion on R2n, then its radial component follows a Bessel process of order 2n. So in all 3 cases, you gain like 1 order compared to the Riemannian situation. Okay, so you in a way can think of those spaces as kind of model spaces for this hypersurface in a contact sub-Riemannian manifold. And one last thing I want to highlight, because this is something where maybe at some point I would like to gain some better understanding of, and that's not included in the work with Davide, is to try and understand or get a better understanding of those characteristic points. Because what we've done now is that for particular model spaces, we have an idea of what happens with the stochastic process around those characteristic points. But the examples I showed off, even in the 3-dimensional case, don't tell you the full picture of what could possibly happen. So even in the higher dimensional case, we won't have captured all possible behaviors around the characteristic points. And so again, this is now the joint work with Davide Ugo and Daniele Canassa. So if we are in the 3-dimensional case, you have again your 2 vector fields appearing, which span your rank 2 distribution. And U is a function which characterizes your surface as like the 0 set of this function U. And it turns out that you can use this Hessian to give a characterization of those characteristic points. So there's something called an elliptic characteristic point and a hyperbolic characteristic point in this 2-dimensional picture, where elliptic is defined as this Hessian at the characteristic point, the determinant of the Hessian at this characteristic point being positive, and hyperbolic meaning that the determinant of the Hessian at the characteristic point is negative. And I'll show some pictures on the last slide. But the interesting thing is that, again, take your intrinsic sub-Laplacian, consider the associated stochastic process, then it turns out that all the elliptic characteristic points are inaccessible. And this is all the pictures we saw early on are where you have an elliptic characteristic point, because in the paraboloid and the sphere, your stochastic process never managed to hit these points. But now, if you consider different surfaces, you can come up with hyperbolic characteristic points. So for instance, if you take like a parabolic hyperbolide and the Heisenberg group, you can end up with hyperbolic characteristic points. And then what happens is that, so in the hyperbolic case, locally around your characteristic point, you're of the saddle type. And then if you start on one of those separatories, you can hit your characteristic point, which is different to the elliptic characteristic point. So there's something, we thought it was nice because actually the stochastic process like exhibits a phase transition exactly at the situation where you change from an elliptic to a hyperbolic characteristic point. And the analysis for this so far, for surfaces in a three-dimensional case, heavily relies on the fact that we have a very good understanding of how two-dimensional dynamical systems behave, which is a property we lose in the higher dimensional situations. So that's why this seems very nice, but a lot of this is going to break down if you want to gain an understanding for the higher dimensional case. And what you can do here is look at the eigenvalues of this matrix. So this is now not the Hessian, but it's the Hessian multiplied by essentially a complex structure you obtained from somewhere. And we sort of normalize this so that this x0, which was the bracket of x1 and x2, essentially meaning the trace of this is 1. And normalizing means because the surface is given as the level set of u, we have a choice of how we choose u. So that's why we choose u, so that at the characteristic point we want to gain understanding of, this x0 applied to u evaluated at x is 1. But yeah, it means that the trace of this matrix is 1, meaning that the two eigenvalues we have add up to 1. So if we want to look at the eigenvalues, there's essentially three things which can happen. They are either complex conjugate, and they need to have real part 1/2, because they need to add up to 1. They could be both real and positive, and then they're sort of symmetric around this line 1/2. So this might be hard to read, but this is like the line 1/2. And then because we're excluding the situation where the determinant is 0, we can't have a 0 eigenvalue. So the third case which can happen is that one of the eigenvalues is negative, and then your other eigenvalue is strictly bigger than 1. And on the dynamical system side, this means that locally, or if you localize around your characteristic point, you have a spiral type. Here you have something which is called a node. And then the last case is you have this so-called saddle. So I should highlight that because there's sort of different terminology in contact world and dynamical system world. So those two are elliptic characteristic points, and this is the only hyperbolic characteristic point. And now the question of if you hit the characteristic point or not depends on the behavior of your drift term, which was this function b. And all the cases we saw explicitly is that if you move along your characteristic point using arc length, then very close to your characteristic point, you behave like 2 over s. That's what we've seen early on. Then if you go for a node and a hyperbolic characteristic point, then this is actually where you see where this 2 arises from, because this 2 is actually 1 over the real part of your eigenvalues. So what you're actually seeing close to your characteristic point in the drift term is 1 over this lambda is, where lambda I is the eigenvalue which corresponds to the this leaf you're currently on. And then the reason why there's a phase transition here is that basically you get very close to the characteristic points, you get different types of Bessel processes. And now a Bessel process of order strictly bigger than 2 is guaranteed to not hit the characteristic point. And the moment you're below 2, which you can check exactly corresponds to this case because suddenly one of your eigenvalues is strictly bigger than 1. This is then going to have some positive probability of hitting the characteristic point. But the upshot is, so this picture is well understood in the surface inside a three-dimensional case, but at the moment we don't really have a good approach of how to get a better understanding of the dynamics around the characteristic points in the higher dimensional picture. And that's where I would like to stop. Thank you very much.